Welcome everybody. My name is Soma. In this presentation, I will be talking about auto-generation of diagnostic assessments and their quality evaluation. I represent Embibe. Embibe is an award-winning AI-driven edtech platform. Its mission is to improve the learning outcomes of millions of learners across the spectrum, across the globe. Embibe's philosophy is that learning is a very holistic experience. Therefore, we not only have to look at the academic aspects, but also the behavioral aspects of the learning process. So we have to measure and track that kind of signals and use them to nudge the learning process to positively influence the learning outcomes. As it is well known, assessments play a very central role. They should be very accurate, meaning they should estimate the latent abilities of the students as accurately as possible. They should be highly discriminating, meaning they should be able to separate the low performing students from the high performing students and everyone in between. They should also take less time. That is, with minimal number of questions, we want to accurately gauge the learning state of a particular student. In this work, we consider various policies to assemble question papers, assuming that we have access to thousands of questions in a database. Here is the data that we consider. On the pedagogic dimension, we consider subject, chapter, and concept of an item. On the behavioral dimension, because we have access to millions of attempts data of a user on a particular item, we can compute quantities such as wasted attempts ratio. That is, how often students spend on a question that is incorrect for them. Likewise, do they spend more time than is desired, which leads to and they get it wrong, that leads to overtime incorrect ratio. Likewise, we can compute many several attributes along the behavioral dimension. Finally, on the classical item response theory side, we can compute difficulty and discrimination parameters of the items in the item pool. We use 2PL model, which is nothing but a logistic regression model with a very specific covariates to estimate the difficulty and the discrimination parameters along with the abilities of the students. We implement the 2PL IRT model via neural networks. The benefits are manifold. First, neural networks are very scalable. You can train them on CPUs or you can train them on GPU forms. Secondly, we can also handle missing data quite effectively. That means we don't have to have the every user and item pair to be observed. We can handle missing data quite well. So in this particular case, both users and items are one hard coded. And you see two simple perceptrons with a simple assembly block. That means we can squarely interpret the weights of the neural network as the desired item parameters coming from a 2PL IRT model. In some sense, we can say this neural network architecture is explainable and interpretable in the parlance of classical IRT. Roughly, this is the sketch of the algorithm to assemble a question paper reflecting some desirable characteristics. Those desirable characteristics are specified via configurable policies. We come back to what those configurable policies are in a little while. So we specify the composition of the question or a test paper, and we form a query. We hit the database with that said query, and we evaluate the results. In case a query cannot be fulfilled, we have to expand the query and hit the database again. This is an iterative algorithm. We use genetic algorithms for query optimization and for query expansion, which is not in the scope of this particular talk. In this particular talk, we only talk about the policy that reflects a desirable characteristics of a question paper. Fulfilling the query is somebody else's job. We consider three policies in this work. The first one is a baseline policy. We already assume that we have thousands of questions in our database. First, via hard constraints, we specify that the test paper needs to come from a particular chapter, it needs to cover a certain number of concepts, coming from a certain chapters. This covers the pedagogic dimensions, which are mostly hard constraints. Once a set of questions satisfy the hard constraints, we still have a choice. They can come from they can come with varying levels of difficulties, discriminations, and behavioral parameters. We then simply choose one question at random of the remaining attributes available at our disposal. That is the baseline policy. In the discrimination only policy, represented by pi DOP, in addition to the baseline policy, we also specify that the questions should have highest discrimination available. In the paper, we showed that if a question paper satisfies this particular policy, then it is D-optimal. In the third policy, in addition to the baseline policy, which considers the pedagogic aspects, and the discrimination only policy, which considers the difficulty and discrimination parameters of the questions, we also consider the behavioral aspects. We might be able to say 20% of the questions should induce wasted attempts for students. Another 20% of the students should induce overtime incorrects, and so on and so forth. The hope is that when a question paper is designed or assembled that reflects these behavioral parameters, it will be a lot more realistic. Once we have assembled a question paper, how do we evaluate? If we have access to the ground truth abilities of the students, then we can compare the estimated abilities to the ground truth abilities via RMSE. Likewise, we can also say that the estimated abilities shall be rank invariant, meaning if two students are ordered in one particular test with respect to their abilities, the ordering shall remain the same even in a different test. This is a desirable feature to have. And finally, we can also use scatter plots and hexagon plots to visually inspect the data patterns along with the RMSE. In this case, we consider these three policies. We have a set of 312 students that are common across all the three different tests administered or configured by these three different policies. Each question paper has about 75 questions with a maximum marks of 300 and a minimum marks possible of minus 75. This is the score, average score that people do get in those three tests. As you can see here, we plot the kernel density estimate of the score distributions of coming from the three different policies. As you can notice, both the DOP and the DBP, the policies which consider the discrimination parameter in the query composition, have the highest spread. It is a reflection of the fact that because the items are discriminating, when these question papers are given to the students, it will elicit a variety of scores. That means the test is able to discriminate students from the low performing to the high performing ones compared to the baseline policy. Here we show the relative rank correlations. Notice that the baseline policy has the lowest rank correlation, and the DOP and DBP are comparable and have higher rank correlation compared to the baseline policy. It shows that students' abilities are more or less remaining rank invariant across the different tests, governed by different policies. Here we show the two-dimensional histograms via hexagon plots. On the x-axis, you see the true ability, which is assumed known, the ground truth. On the y-axis, you see the estimated ability. Compared to the baseline policy, both in DOP and the DBP, we see that the estimated abilities nicely align with the ground truth abilities, and which indicates that the RMSE is lower for these two policies compared to the baseline policy. Instead of using simulated data, in this case the data is real, but we assemble a test and we consider the same students who are observed beforehand. Instead, we roll the two tests coming from the baseline policy, one coming from the baseline policy and the other coming from the DBP policy, and give it to students on a real test. And we notice that The difference between the 95th percentile and the 5th percentile as a measure of spread is actually higher for the DBP policy, which indicates that the test generated with DBP policy is having better discrimination ability, as it is shown in the kernel density estimates. No, it has a longer tail. The DBP policy has a longer tail compared to the baseline policy. Likewise, we also show the RMs, the scatter plots, and in the paper we showed that the MSE is actually smaller for the DBP compared to the baseline policy. So based on these observations, we note that if a test is configured with both DBP and DOP, it has a higher spread, it has a better accuracy, and the relative rankings of the abilities remain more or less invariant to the different tests, unlike the baseline policy. So in conclusion, we proposed three different policies which are extensible to assemble a test paper, assuming that we have access to thousands of questions in the database. We validated those policies both by simulations and by administering real tests to real users. And we found that DBP and DOP are comparable and perform slightly better compared to the baseline policy. We note that in the IRT, we just considered the classical 2PL model. But because we postulated the estimation of the item parameters via neural networks, it is possible to extend them to include behavioral parameters. We hope that such kind of enriched IRT models will reflect the reality better, and consequently, both DBP and DOP can do better. That means we can administer and assemble tests which are a lot more realistic and which go beyond the classical ART paradigm. We like to thank Anwar Sheikh and Nishit Desai and their teams for helping us conducting the pilot studies. The references are available in the paper. Finally, any questions, we'll be happy to take. Thank you all.